Can
Press it. There you go.
Okay, is this okay now? I think now it's recording. Yeah. Um, so yeah, I attended Goals last year and it was an awesome experience. And I guess today going to be talking about the hyperfinite to one factor. I'm going to construct it and talk a little bit about this stuff. Yeah. So let's start by recalling a few things because I guess just listening to hyperfinite to one factor just sounds like there's a lot going on. So just I wanted to recall a few things before getting into the construction. So everyone can hear me, right? Like I'm audible.
Yeah, I can hear you.
Okay. So just to recall what a factor is, so if you have a von Neumann algebra where the center Z of M is trivial, M intersection, the commutant of M is trivial, then that's called a factor. And you guys saw the type decomposition theorem yesterday where um, like basically a corollary of the type decomposition theorem is that any factor is going to be of one of the three types, type 1, type 2, or type 3. Um, so what do you mean by type 1? It means that every non-zero projection has an abelian subprojection. And then type 2 is interesting. It means that the von Neumann algebra is semi-finite and it has no non-zero abelian projections. So I've made a little bubble on the side about what semi-finite means. Semi-finite means that you have a family of pairwise orthogonal finite projections, let's call them PI, such that the identity is equal to the sum of this family of pairwise orthogonal projections. And if I want to say that it's of type 2, 1, then it's finite and it has no non-zero abelian projections. And then there's another type which is type 2 infinity, which means that it's properly infinite. And then finally there's type 3, which is purely infinite von Neumann algebras. So what we are going to be looking at is we're going to look at factors type 2 and then in particular type 2 1 factor, and we're going to construct a we're going to construct a 2 1 factor and it's going to be called the hyperfinite 2 1 factor. Okay, so for any natural number, let's embed the matrix algebra MNC into M2NC via this embedding, which I'll call phi n. And how do I do this embedding? I embed a matrix A into a matrix double of its size by the embedding A0, 0, A. And as we can see, phi n is injective because if the image is the zero matrix, then the like the thing that is going to be sort of mapped to the zero matrix also has to be the zero matrix. So it's injective. It's a star homomorphism because phi n of A star is going to be phi n of A star. Again, just taking adjoints. And then phi n of AB is equal to the matrix AB 0, 0, AB, which is equal to phi n of A times phi n of B. I'm trying to give details because, yeah, I feel like it's super helpful in sort of seeing what exactly this embedding is and what we need to do after that. Also, we have that phi n preserves the norm. We consider the operator norm here of a matrix, that is norm of a matrix A is equal to the supremum of norm of AX, where you're taking the supremum over the vectors of like size 1. And why does it preserve the norm? So let's consider the image of a matrix A, right? Like let's double the matrix A and let's look at A tilde, which is A0, 0A. We want to show that the norm of A tilde is equal to the norm of A. So how do we go about showing that? Let's consider a vector of in C2n, where that vector is x1 and x2, and x1 is in Cn, x2 is in Cn. So then if we look at A tilde x, that gets mapped, again, A tilde is A0, 0A. When we evaluate at x1, x2, it becomes just AX1 and then AX2. So now if we're finding the square of the norm A tilde x using the definition and the fact the Pythagorean identity, we have that A tilde x square is equal to AX1 squared plus ax2 squared. And then that's less than equal to the norm of a squared, and then the norm of x1 squared plus x2 squared, which again, it adds up to the norm of x squared. So we have that the norm of a tilde is less than equal to the norm of a. And then to show that the norm of a is less than equal to the norm of a tilde, we can just consider any y in Cn, which has, like any vector in Cn, which has a length of 1. And then we define like your vector x to be y and 0, where for the first n entries you have y, and then the next n entries you have 0. So then a tilde x is going to be ay and then 0. And then norm of ay is equal to norm of a tilde x, which is less than equal to the norm of a tilde. Taking the supremum over all these y's, which have norm equal to 1, you get that the norm of a is less than equal to norm of a tilde. So just, again, sort of zooming out, I guess what I want to say is this map, this embedding, it is an injective star homomorphism which preserves the norm. Also, it preserves the normalized trace. And why is that? If I look at 1 over 2n times the trace of a00a, that's equal to 1 over n times the trace of a. So it preserves a lot of things, and hence we can consider the sequence of inclusions of M2C, which is like, again, you consider the embedding into M4C, and then consider the embedding into M8C, and so on and so forth, into M2 to the power NC, and consider the inductive limit. So we define R0 to be the inductive limit of these finite dimensional matrix algebras. So union of all the overall n of M2 to the power NC. Is this okay so far? Okay. So now let's just make a few notes about what this R0 is, right? We are taking the inductive limit of finite dimensional matrix algebras. So we note that it's a star algebra, right? Because all the finite dimensional matrix algebras are also star algebras. It has a norm which is carried over from the matrix algebras. It's not complete, right? Because if you look at like the limit of finite rank operators, it's also compact operators, but that's not there in R0. It's just a union. So it's just a star algebra with a norm, and it has a linear functional that sort of carries over from the normalized trace. So you have a map, a linear functional tau 0, which is from R0 to C, which is defined as like tau 0 at x is equal to 1 over 2 to the power n of the trace of x when x is in m of 2 to the power nc. So basically, at any element of m2 to the power nc, we're just taking the normalized trace, and that is tau 0. And that's how we define it. And because we have that the phi n's preserve the normalized trace, this is like a well-defined, nice linear function. So using the properties of the normalized trace, we can conclude a few properties about tau 0 as well. So what can we conclude? We can conclude that tau 0 is unital because the trace is unital, and so the normalized trace is unital. And when we're taking the inductive limit, we have that tau 0 of 1 is equal to 1. It's positive because if we take any element in R0, then tau 0 of x star x is greater than equal to 0. Again, because we have all these properties, these nice properties of the trace. It's faithful, that is tau 0 of x star x is equal to 0 if and only if x is equal to 0. And then it's also tracial, which is that tau 0 of xy equals tau 0 of yx for any x and y in R0. Next, I want to do the the GNS representation h pi of R0 and tau 0. Basically, what I'm doing is I'm going to complete R0, and that completion of R0, I'm going to call it H. And R0, I'm going to consider it to be equipped with this inner product, that is x comma y is equal to tau 0 of x star y. It's basically the GNS representation as we know it. Just, I guess, a small subtle nuance is that every time we've done GNS representation, we've done it for like C star algebras, I guess. But it can follow in the same way for like just a star algebra. Everything is follows in the exact same way. And this is just, I guess, a subtle nuance I wanted to point out. So yeah, H is the completion of R naught equipped with this inner product. And you have the representation pi, which goes from R naught to B of H. It's an injective star representation. And you have pi of x, where x is in R naught, acting on any y in H given by xy. So R naught is a dense subspace of H because we're completing R naught, and then that's going to, the completion of R naught is H. We define R to be pi of R naught and then the double commutant. Or because of the bicommutant theorem, we can also call it like the SOT closure of pi of R naught or the WOT closure of pi of R naught. All of them would be the same thing. So that is what we're defining R to be. And now this R is called the hyperfinite 2-1 factor. So we need to show that it's a 2-1 factor. And that is what we're going to go about doing. So the construction is done now of the hyperfinite 2-1 factor. That's basically, again, the double commutant or the WOT closure or the SOT closure of pi of R naught. And that's an element, I mean, that's an algebra in B of H. So let's go about showing that it's a 2-1 factor. So the first thing is we think of 1 in R naught as a vector in H, right? So 1 is cyclic for R because of the GNS construction that we've had, like R times 1 is dense in H, just by the definition and the construction of that cyclic vector. So 1 is going to be like a cyclic vector for R as well. Okay. And we also have that it's separating for R. Why? So let's fix any vector A in R naught. Then for any Y in R naught, let's consider the L2 norm of YA and then square that. By the definition of the GNS construction, that's equal to tau naught of A star, YA, which because it's tracial, I can move the A star to the back. So that's going to be Y star, A star. And then again, I can move the Y star to the back. So that's going to be tau naught of A star, Y star, which is less than equal to the norm of A square tau naught Y star. So the reason for this is I've written in parentheses on the side that A star is less than equal to norm of A square times 1. And as a result of that, because tau naught is a positive linear functional, it's like a state, we have that Y star is less than equal to like, when it's evaluated at Y star, it's less than equal to norm of A square times tau naught of Y star. And then that is equal to norm of A square times the L2 norm of Y square. So we have that YA squared, the L2 norm of YA squared is less than equal to norm of A squared times the L2 norm of Y squared. So basically, what do we get? We get that if we have any y in R naught, what this inequality tells us is that if we have any element of R naught, multiplying on the right gives us a bounded operator, right? If we multiply on the right by any element of R naught, we get a bounded operator. So if we view R naught as a dense subspace of our Hilbert space, multiplication by A on the right tells us is a bounded operator because of this inequality. And in fact, it extends to a bounded operator on B of H because H is a Hilbert space. So we can do that extension. And we call it rho of A. So rho of A is the operator which acts on any element by multiplying it on the right by A. And we also have that this element is in the commutant of R. Why is that? Because you're multiplying on the right here by an operator. So what R does is it multiplies on the left. So if you're multiplying on the left or multiplying on the right, it doesn't matter. Like you can interchange the two order of the operations. So rho of A is R prime. Rho of A is in the commutant of R. Any questions so far? Okay. Um, so then let's define a linear, oops, yeah, let's define a linear functional tau from R to C. And the way I'm defining this linear functional is at any element x, just let's recall, since R is in B of H, x is an operator, we're thinking of all these as operators. So that is equal to x evaluated at 1, and then that inner product with the unit 1, and then the inner product of that. So this is a linear functional. Let's, I hope that that's okay. You can verify that this is a linear functional. And we're going to show that this is in fact a WOT continuous faithful tracial state. So let's look at each of those things, WOT continuous and then faithful tracial state. So let's look at the faithful bit first. So suppose you have any element such that, yeah, suppose you have any element x in R such that um, tau of x star x is equal to 0. So what does that mean? If I have tau of x star x, that's equal to the inner product of x star x evaluated at 1, comma, the inner product with 1. And then by the definition of x star, I can move the x star onto the right. So that's going to be the inner product of x at 1 and x at 1. And then if I say that tau of x star x is equal to 0, that means this inner product is equal to 0, which means that x of 1 is equal to 0. So if I have any element A in R naught, what I would have is that the, like if I multiply rho of A with that vector x at 1, that's equal to 0. And because rho of A is in the commutant of R, so I can interchange the order of rho of A and x. So that's going to be equal to x times rho of A evaluated at 1. And then rho of A at 1 is just going to be A because it's just right multiplication of 1 by A, which is going to be A. So that's equal to XA. So I have that XA is equal to 0. And now because R naught is dense in H, so I'd have that XC is equal to 0 for any C in H, which would mean that just the element X is equal to 0. And so that would tell me that tau is faithful. Also, it's a vector state because tau of 1 is equal to 1 acting on 1, and then it's in a product with 1, which is equal to just 1. It's WOT continuous because if I have any xi converging to x in WOT, then just by the definition of WOT continuity, just by the definition of what it means to converge in WOT, I'd have that xi 1, comma 1 converges to x evaluated at 1, comma 1. And so then tau of xi converges to tau of x. And then it's tracial because for any x in R naught, I'd have tau of pi of x is equal to tau naught of x. That's just the definition. So if I consider any x in R and y in pi of R naught, I can find a net in pi of R naught which converges to x SOT, right? I can find a net of elements xi in pi of R naught which would converge to x SOT. And then since pi of R naught is SOT, that is because pi of R naught is SOT dense in R. And so what I would have is tau of xy is the limit of tau of xiy. And then because xi and y can be interchanged and flipped, because I know that like tau naught is tracial, so I can flip it there. And so that's going to be tau of yxi, which again, when I take the limit in SOT is going to be tau of yx. And then similarly, I can approximate y by yi in pi of r naught. So I would get that, in fact, this tau that I'm defining on the hyperfinite factor to one factor r, that is going to be tracial. So tau of xy is equal to tau of yx for any x and y in R. Okay, now the next thing that I would want to show is that, yeah, wait, hold on, what just happened? Uh, Yeah. So now let's consider any z in the center of R. Okay. So I define a linear functional from R to C given by C of x is equal to tau of xc. Again, there are like many different functionals that are getting constructed. So let me know if you have any questions. So I'm defining phi of x as tau of xz where z is in the center of R. So I want to show now that this linear functional is tracial. How do I go about doing that? I have phi of xy is defined as tau of xyz. And because z is in the center, because tau is tracial, I can interchange yz and x. So I put yz in the front and x behind. So that's equal to tau of yzx. And then that is equal to y times xz because z is in the center, which is equal to phi of yx. So I have that phi is also tracial. And then if I restrict phi composition pi to m of 2nc, I get a tracial linear functional. So there's a bubble at the bottom, which is something that I'm going to use. It's an exercise given in the W star notes, and I'm not going to prove it because it's sort of just computational, but I'm just going to state it right now and sort of mention that, hey, this is what I'm going to use. So you can try the exercise, but just letting you guys know that this is what I'm using. The thing that I'm using is, suppose I have a tracial linear functional from a matrix algebra MD of C to C, then the result is that that linear functional is equal to the linear functional evaluated at 1 or the identity matrix times 1 over n times the trace, which is like a super powerful result if you think about it. And so because this phi composition pi that I have above, it's a tracial linear functional. So then phi composition pi is equal to, by this result, it's phi composition pi evaluated at 1 times 1 over 2 to the power n times the trace of x. Now, if I look at the first few terms, phi composition pi of 1, that is just the tau of z. That's like just by the definition of tau, it's going to be tau of z. And then the next part, 1 over 2 to the power n times trace of x, that's going to be tau of pi of x for all x in the matrix M2 to the power nc. And since this holds for any n, basically any matrix that I get, no matter how big the size is, this is going to hold for all natural numbers n. I have that phi of x is equal to this equality holds. It's going to be tau of z times tau of x for all x in pi of r naught. So I have like a really nice inequality a really nice equality that holds. Okay, so now I have that this holds for all x in R, right? Like phi of x is equal to tau of z times tau of x for all x in R. How do I get that? Using the SOT denseness of pi of R naught in R. Just go on to like R extended the inequality to R using the SOT denseness. And so for all x in R, I have that tau of xz is equal to tau of z times tau of x. I have this equality that I get like tau of xz can be sort of factored into two things, which is tau of z times tau of x. And then if I move it over to the left-hand side, I can write it as equivalently as tau of x times z minus tau of x is equal to 0. And this holds true for any x in R, right? So if I pick a particular x in R that I want, which is going to give me a nice result, I can do that. So in particular, if I choose x to be z minus tau of z star, the faithfulness of tau is going to give me that like z minus tau of z is equal to 0. That would mean z is in fact a complex number, right? Because it's tau of z, which is a linear functional. Like since tau is a linear functional, tau of z is just going to be a complex number. So that means z is a complex number. And what had we taken z to be? We had taken it to be in the center of R. So since z is in the center of R is in fact just a complex number, we have that R is a factor. So now we have shown that this thing that we had constructed at the beginning, it's a factor. It was quite an elaborate construction, but yeah, like the we have successfully showed that this R is a factor. Now, the things that remain to be shown is that it's finite and it has no non-zero abelian projections. So let's just show that it's finite. Suppose we have that an element in R is a partial isometry satisfying V star V equals 1 and V star is less than equal to 1. So what we would have is tau of 1 minus VV star star times 1 minus VV star is equal to tau of 1 minus VV star. And how do we do that? We get that equality by sort of opening up the brackets inside, because 1 minus VV star star is just going to be 1 minus VV star. And then again, just evaluating the brackets and using the fact that V star V equals 1, we would get tau of 1 minus VV star. Now that is equal to tau of 1 minus tau of VV star, which is equal to tau of 1, and hence I would get 0. So because, again, I have that tau is faithful, I'd have 1 minus VV star is equal to 0, which would mean VV star is equal to 1, and hence R is finite. Now I would want to show that R has no non-zero abelian projections. That's the part that remains to be shown. So how would I show that R has no non-zero abelian projections? This is the last bit, which I would say it involves a sort of an argument that's used before in the goals notes as well. So I would really invite you to read pages 61 to 63 in the goals notes. Like, it's very interesting how these things sort of play out. So let's suppose that R has a non-zero abelian projection. Let's call it P. And that's a non-zero abelian projection in P of R. I'm using a lemma, which I'm sort of giving without a proof, that if I have a factor R, then any non-zero abelian projection is minimal. We already know that for any von Neumann algebra, any minimal projection is abelian. But if you have a factor, then any non-zero abelian projection is also minimal. We have the converse is true. And that's given as an exercise, I think, in the goals notes as well. It can be done using one of the corollaries for like the theorem that PMP and M star P are factors if M is a factor. So the proof is straightforward, but like, I just to avoid sort of derailing the talk, I'm going to stick to this construction. But suppose R has a non-zero abelian projection, then because of this lemma, I have that abelian projection is a minimal projection, right? So let Pi, where I is an indexing set, be a maximal family of pairwise orthogonal minimal projections, right? I just consider whatever the maximal family of minimal projections, which are pairwise orthogonal, is going to be. I call that Pi. It's non-empty. The indexing set is non-empty because I've assumed that R has a non-zero abelian projection, hence minimal. And I define Q to be 1 minus the sum of all these projections, Pi. Suppose Q is not equal to 0. So then by the comparison theorem, I have that Q is less than equal to Pi, the squiggly less than equal to, or Pi is the squiggly less than equal to Q for I in I. And why does the comparison theorem give me this? Because we have that R is a factor, right? So there are only two central projections, 0 and 1. And hence, because of that, only one of two possibilities happens, that Q is less than equal to Pi or Pi is less than equal to Q. So let's look at the first possibility. If Q is less than equal to Pi, then I would have that Q is equivalent to Pi, because Pi is a minimal projection by our assumption. And so I have that Q is minimal because of proposition 4.2.7 in the notes. And this is a contradiction to the maximality of our family. We've assumed that this family Pi is the maximal family of pairwise orthogonal minimal projections, right? And that would be a contradiction if Q is also minimal. So Q squiggly less than equal to Pi is not possible. So if Pi is squiggly less than equal to Q, then what happens? Then Pi is equivalent to some Q naught, which is less than equal to q. This is not the squiggly less than, it's just going to be equivalent to something that's strictly less than equal to q. And so I have that q naught is minimal, which again contradicts the maximality of this family. So I cannot have like my assumption to be true. What was my assumption? That q is not equal to 0 was the assumption. So q has to be equal to 0, which means that this sum pi, um, uh, the sum of the projections pi is equal to 1. Okay. And because of the sum of the projections being equal to 1, like that's a result that we get. Now, since R is a factor and all of these PIs and PJs are minimal projections, I have that PI is equivalent to PJ for any I and J in the indexing set. Again, by the comparison theorem, because 0 and 1 are the only two central projections. I claim that the indexing set is finite. Okay, what happens if it's not finite? If the indexing set for my minimal projections is not finite, then I can partition the set I equals I1 union I2 into like two disjoint sets. The indexing set is going to be divided up in such a way that like the cardinality of I1 is equal to the cardinality of I2, which is equal to the cardinality of I. You can do this, right? If you don't have a finite set. And so you get a bijection sigma from I to I1. Let's set Qi to be P of sigma I. Basically, I'm just labeling it as Qi, but it's P with like evaluated at sigma I. Not evaluated, but P indexed by sigma I. And so I would have that Pi is equivalent to Qi for all I in the indexing set, because of the part that I've written just above my claim of I being finite, that Pi is equivalent to Pj for any I and j. And since Qi is just going to be some Pj, so then I have Pi is equivalent to Qi for all elements in my indexing set. And so this holds for all I and I, which gives me that the summation of Qi is equivalent to the summation of Pi, which is equal to 1 by lemma 4.1.10, which says that if you have two projections are equal in for all projections in a family, then the sum of the family of projections is equivalent to the sum of the family of projections. Okay, so now I have certain calculations. So 1 is equal to the sum of projections Pi, and then that sum of projections can be written up as two sums separately, which is the sum of I in I1 of Pi plus the sum of I in I2 of Pi. And then that is equal to the sum of Q, um, Qi over I in I plus the sum of Pi over I in I2, which is going to be greater than the sum of Qi over I. And this is a contradiction to 1 being finite. You can't have like infinitely many Qi's which are less than 1 when 1 is finite. And we've showed that 1 is finite because we showed it to be finite. So we have that the cardinality of I is some finite number n, which is again finite less than infinity, and we can relabel the projections Pi as just P1 to Pn. And since we have that P1 is equivalent to Pi for all I, we can find a partial isometry Vi in R such that Vi star Vi is Pi and Vi star is P1, just by the definition of two projections being equivalent. And since Vi is equal to P1 Vi, and why is that true? Because Vi is equal to Vi star V1 because it's a partial isometry. That's the definition. And so Vi star is P1. So then that's equal to P1 Vi. For each I, for any x in the von Neumann algebra R, I have x is equal to sum of Pi times x times the sum of Pj, which is all 1. So I'm just multiplying and pre-multiplying and post-multiplying by 1. And then opening up the parentheses, I get that that's equal to the sum of I comma j from 1 to n of pi x pj. And then Writing pi, rewriting pi, I write it as the sum over all I and j from 1 to n of vi star vi x vj star vj by just writing what pi is and writing what pj is. And then since vi is equal to p1 vi, in the next line, what I've written is this sum of I comma j from 1 to n is going to be vi star p1 vi, replacing vi by p1 vi, and then the last term gets changed from vj to p1 vj. And so then the middle terms can be grouped. I can write it as p1 vi x vj star p1. That middle terms can be grouped. And what I would get is that the middle term p1 vi x vj star p1 is going to be some scalar multiple of p1. Why? Because p1 is a minimal projection. So I have x is equal to the sum of vi star and then some scalar times p1 times vj. And so that's equal to the sum of, again, let me just pull the scalar to the front, and then that's equal to vi star times p1 times vj, and then that's equal to xij times vi star vj, because p1 vj is just equal to vj. So now I have x, my element in the von Neumann algebra R, is written as the sum of scalars xij times the partial isometry is vi star times vj. And so if I consider this map from R to the matrix MNC, I mean to the matrix algebra MNC, which is given by f of x, and I use all the scalars as sort of the coordinates of the matrix, or like placing all the xij's according to the aij's in the matrix algebra, that map is injective because if the image is zero, again, x has to be zero by this definition of x and x written as a sum that I have out here. And also I have that if I have f of vk star vl, this is again just a giant computation, but f of vk star vl is going to be the matrix ekl, which is going to be 1 if k is 1 in the kth place and then 0 everywhere else. So I have that this map f is in fact a bijection. Like this map f from R to MNC is a bijection. And we can also check that it's in fact a star homomorphism. So this is an isomorphism between the hyperfinite 2-1 factor and MNC. This is a contradiction, right? Because MNC is like a finite dimensional algebra, but R is infinite dimensional. Why is R infinite dimensional? Because R naught, which was like the inductive limit of the matrix algebras, is infinite dimensional, and then pi of R naught is infinite dimensional. So R is infinite dimensional, but Mn of C is finite dimensional. So that's a contradiction. So you can't have a non-zero abelian projection. And from that, you can conclude that R is in fact a 2-1 factor. So yeah, just proof by contradiction is what gives us that R is a 2-1 factor. And I think that's about all I wanted to say for this. The notes also tell us how when you have like an infinite conjugacy, like if you have gamma, which is like an ICC group, then L of gamma is also a 2-1 factor. And the proof follows, like many parts of the proof follow in the same way. So I would invite you to look at it. But yeah, I can stop sharing my screen. And if you have any questions, you can let me know. I can stop recording.